Welcome to The Explainer. Today we're diving into one of the wildest, most mind-bending ideas in all of science, the many worlds interpretation. It's this theory that says, hey, maybe the most straightforward explanation for, well, everything, is a giant branching multiverse.
So let's just jump right in with a question that honestly sounds like it's straight out of a comic book, but physicists are taking it very, very seriously. Does our reality literally split into countless parallel universes with every single quantum event? Well, if you subscribe to the many worlds interpretation, the answer isn't just maybe, it's a definite yes.
So, you're probably wondering, why on earth would anyone propose something so crazy? And to get that, we have to go back to this huge, messy problem at the very heart of quantum physics. It's called the measurement problem, and it's basically a massive contradiction in how the rules of the universe seem to work.
Yeah, the big trouble is that quantum mechanics, as it's usually taught, seems to have two totally different sets of laws. It's like the universe plays by one set of rules when nobody's watching, but then the instant we look, it switches to a completely different, clashing rulebook. And you know what? They can't both be fundamentally right. Something's gotta give.
Okay, so this slide just lays that conflict bare. On one side, you've got this beautiful, smooth, predictable evolution. Everything just flows according to the Schrödinger equation. You can run the clock forwards or backwards. But then, on the other side, you have wave function collapse. This is what supposedly happens when we measure something. Suddenly, bam, reality just jumps to one random outcome. It's messy, it's unpredictable, and you can't undo it. It really is like the universe has this one weird rule that it only pulls out when it thinks we're peaking.
All right, let's make this even more concrete. There's a famous experiment that really shines a spotlight on just how bizarre this whole active-looking thing truly is.
And this is it, the double-slit experiment. It shows the mystery in all its glory. So, you fire one little particle at a time. If you don't watch which slit it goes through, it acts like a wave. I mean, it somehow goes through both slits at once and creates this beautiful interference pattern on the screen behind it. But, and this is the kicker, the second you put a little detector there to see which slit it went through, its whole wave act just vanishes. Poof! It starts acting like a normal little bullet, making two simple stripes. The simple act of measuring seems to fundamentally change what reality does.
So what's going on here? How do we explain this? Well, the traditional view, the Copenhagen interpretation, basically says our measurement forces this mysterious collapse, all the other possibilities just evaporate, and only one becomes real. But many worlds comes along and says, wait a minute, what if nothing disappears? What if the universe doesn't collapse, it just branches? In one universe, the particle went left. In another, totally separate universe, it went right. Both things actually happened.
And this idea, this branching, leads us straight to the genius and, honestly, elegant solution that a physicist named Hugh Everett III came up with way back in 1957. His approach was just stunningly simple. He looked at the problem and decided to solve it by just throwing out the part that didn't make sense.
Everett's big, bold idea was this. What if that weird, random, jumpy collapse rule is just made up? What if it's not a real thing? What if the universe only ever follows that one smooth, predictable rule, the wave equation, all the time, with no exceptions? No special cases for when we're looking, no exceptions for anything.
And that right there, that is the absolute heart of the many worlds idea. Because if there's no collapse, well then, what happens to all the other possibilities? They can't just disappear into thin air. If the math says they're there, then they must be physically real somewhere.
And that is where the multiverse comes crashing in. Instead of one possibility winning out, the universe itself just splits. The tree analogy is perfect. Every time there's a quantum event, the trunk of reality grows new branches. Each branch is a different outcome. So there's a branch where the particle went through the left slit and another completely real branch where it went through the right. All of them are equally real.
Okay, I know what you're thinking. This raises a massive, blinking neon sign of a question. If all these other worlds are real, why do I only experience this one, right? Why don't I feel myself splitting into a million different versions every second? It's a fair question.
And the modern answer, which actually came a bit after Everett's original idea, is a process called quantum decoherence. And this is super important. This isn't some philosophical hand-waving. Decoherence is a real, measurable, physical process that we can actually see happen in labs.
So here's how it works, more or less. Any quantum system, an atom, a particle, even you, is constantly bumping into its environment.
When it does that, its quantum information kind of leaks out and gets tangled up with everything around it. The environment then naturally filters out the weird, fuzzy states and favors the stable, classic-looking ones. This whole process happens unbelievably fast, and it's what causes those branches of reality to split and become totally isolated from each other. They can't talk to each other anymore. They've effectively become separate worlds.
So what this all means is that the collapse isn't a real event, it's an illusion. It's just what a branching universe looks like from the inside, from our limited perspective. See, we're made of quantum stuff too, so we get tangled up and decohered right along with the experiment. We get locked into one of these branches, and from our point of view, it looks for all the world like the other possibilities just vanished. But they didn't. They're just on another branch that we can no longer see or interact with.
All right, so let's pull back for a second. What does all this mean in the grand scheme of things? How does this many worlds idea really stack up against the other ways of thinking about quantum mechanics?
You can see here that many worlds is kind of the odd one out, but in a good way. It's known for its mathematical purity. It treats the wave function as a real thing, and it insists its evolution is always deterministic and predictable. There are no weird special rules just for observers. You, me, a rock, a supercluster of galaxies, we're all just quantum systems following the exact same single law. In a sense, it's the interpretation that trusts the core math of quantum mechanics the most.
So here's the big takeaway, and it's a bit of a twist. Even though it sounds wild, the many worlds interpretation isn't about adding crazy new stuff to physics. It's actually the most conservative theory. Think about it. It solves that huge measurement problem by removing a rule, the collapse, that was only added in the first place to make the weirdness fit our everyday intuition. Many worlds is what you get when you just take the basic math of quantum mechanics and say, okay, let's just see what happens if this applies to everything, no exceptions.
And that leaves us with a really profound thought to chew on. Could it be that the universe is actually incredibly simple, governed by just one beautiful, elegant, deterministic law? And what if all the randomness, all the mystery, all the quantum weirdness that we struggle with isn't really there? What if it's all just an illusion, a product of our very limited viewpoint, stuck here inside just one branch of a truly magnificent, infinitely branching multiverse?